Hello everyone, I'm Harshavardhan, but you can call me Harsha. And today I would like to present our work on vFPIO, which is an FPGA-based I/O acceleration framework with a focus on programmability and portability. So this work was done in collaboration with my co-authors at TU Munich, mostly with Jiyang, Atsushi, and my advisor Pramod. So let me first begin by motivating the need for vFPIO. So as we all know, CPU-centric applications, they cannot fully take advantage of the performance benefits offered by high-speed I/O devices such as SSDs and high-speed NICs. To overcome these issues, cloud providers are increasingly incorporating smart I/O devices that contain units of computation on the I/O device. So applications can then offload computational tasks to be executed on these units, thereby improving performance and reducing the unnecessary movement of data. FPGAs are an excellent choice for such units of computation, as they enable high-performant I/O processing in a flexible manner. Such FPGA-based I/O acceleration is becoming increasingly popular in the cloud, with examples such as Azure Boost and Google's Titanium project. So a typical FPGA application that is offloaded to the FPGA is encapsulated within a user logic, which is written in a hardware description language. So the user logic consists of two components. So firstly, it consists of a computational logic, which is I/O independent, and an I/O-dependent I/O glue logic, which interfaces with the I/O controller that speaks to a specific I/O device that is attached to the FPGA. And additionally, on the host CPU side, we have a software library which is used by the CPU side of the application to control the execution of the user logic on the FPGA. However, the problem with this is that the application developer, that is the developer who builds the user logic, must be aware of the low-level interfaces on the FPGA. And additionally, there is no support to run the multiple user logics at the same time. So to overcome these issues, FPGA shells such as Coyote have been introduced, which enhance the programmability and isolation when running multiple user logics on the FPGA. So to do this, the FPGA region is divided into a static part, which is fixed at compile time, and a dynamic region, which can run one or more user logics of the application. So the static region, it contains the shell, and is responsible for abstracting away the physical interfaces of the FPGA. And among other things, it consists of an I/O arbiter or a scheduler, which is responsible for isolating access to shared FPGA resources, and the I/O controllers for one or more I/O devices that are attached to the FPGA. And in the dynamic region, there is one or more partially reconfigurable regions, which can be used to offload and execute the user logic, which consists of both the computational and the I/O logic. And as before, on the host side, we have a library, rather a runtime library, which helps the host side application to control the execution of the user logic on the FPGA. However, the problem with this is that these shells directly expose the low-level I/O interfaces of the I/O devices to the FPGA without any I/O virtualization. And this introduces three challenges when a programmer wants to design their user logic. So firstly, existing shells make the programmability of user logics that want to use I/O devices very hard. So this is because the shells only expose low-level I/O device interfaces, and the programmer must understand these interfaces for every I/O device that they want to use. And because the programmers are forced to use the low-level I/O device interfaces, the user logic which they write is not portable across multiple I/O devices. So this basically means that even if the computational logic remains the same, the entire user logic must be rewritten, and this is not good. And additionally, existing shells do not isolate I/O performance, rather in the sense that they do not provide any performance isolation when more than one user logic try to access the same I/O device. So this could lead to a degradation in the I/O throughput, and this could be bad for a performance-critical application. So the problem we are trying to solve in this work is how can one design an FPGA-based I/O acceleration framework that enhances programmability, portability, and ensures a performance isolation of user logics on the FPGA. So we present vFPIO, which is a portable and easy-to-use FPGA I/O acceleration framework. And vFPIO's design adheres to 3 goals. So firstly, we want to improve like the programmability of both the user logic as well as the host-side application logic. Additionally, we want to make sure that the user logics that are written by the application programmers, they can be written in a portable manner across multiple I/O devices. And finally, we also want to ensure the performance isolation when more than one user logics access the same I/O device. So to do this, vFPIO includes 3 components. So firstly, we have a hardware component called the virtual I/O module, which must be compiled into the user logic even before offloading it to the FPGA. So the virtual I/O module provides a virtual I/O interface through which the user logic requests I/O. In the static part, we have the vFPIO shell, which includes the vFPIO I/O scheduler and a bunch of I/O controllers for the I/O devices. So the vFPIO scheduler intercepts I/O requests from the user logic and picks an I/O request based on a predefined, pre-configured scheduling policy. And additionally, we have the vFPIO library on the host, which, among other things, enables the host-side application to dynamically change the I/O paths between the user logic and the target I/O device and configure the scheduling policies in the shell. So now that I've motivated the need for vFPIO, next let's take a look at some of the challenges that we had to overcome in its design. So firstly, existing shells pose programmability challenges. And this is because they directly expose low-level I/O interfaces to the user logics. And usually these interfaces are grouped through like an I/O protocol like ATC. This additionally leads to a fixed number of I/O ports and a fixed I/O width, which may limit programmers' flexibility in terms of how they design their application. And the problem with this is that the programmers now need to understand the low-level I/O interfaces of every device that they want to write the user logic for. And they end up writing a one-off user logic that contains the I/O-specific logic for the specific I/O device. So to overcome this challenge, we have designed the virtual I/O module, that enables device-agnostic I/O accesses by abstracting the physical I/O ports into virtual I/O ports. So on the user logic side, the virtual I/O module exposes virtual I/O ports, and the user logic issues I/O requests through the virtual I/O ports. And additionally, the virtual I/O module, it enables the user logic to switch to another I/O device at runtime through the I/O switching mechanism that is provided within the module itself. Additionally, the module exposes a control interface that enables the host side part of the application to reconfigure the I/O path on demand by writing to a few hardware registers within the virtual I/O module, and upon doing so, the user logic can immediately switch to a new I/O device. The next challenge is with respect to portability of user logics across multiple I/O devices. So as I mentioned previously, because of these low-level I/O interfaces, now the user logics are forced to use them in their application, and this basically leads to the tight coupling of the computational and the I/O logic within the user logic itself. And what this means is that at the end of the day, you would end up writing a user logic which is specific for a particular I/O device. And this results in portability issues across multiple I/O devices, in the sense that even if the computational logic remains the same, you would have to reprogram the user logic, you would have to recompile it, and you have to re-offload it to the FPGA. And this is very, very expensive in existing FPGAs. So to overcome this problem, we have a vFPIO library within the vFPIO framework, which provides a software-based approach to dynamically reconfigure the I/O path between a user logic and a target I/O devices on demand. So the vFPIO library is a host-side library, and it allows the host-side applications to configure the I/O paths on the FPGA on demand. And this basically it enables I/O path reconfiguration without having to reconfigure the whole user logic. And additionally, the library includes APIs, wherein the I/O devices are represented as files, and they are also so basically the interaction between the host-side library and the device is also represented as files. And the final challenge arises because of the lack of performance isolation between multiple user logics. So when multiple user logics share an I/O device, the I/O throughput for the performance critical applications can degrade a lot because the existing FPGA shells, they equally divide the I/O bandwidth between the user logics. So basically what this means is that for high priority applications, we need a priority-based scheduling mechanism for the I/O transactions, wherein we execute the high priority applications first, and additionally provide the mechanisms to pause and resume the low priority applications without any errors. So to do this, we have an I/O scheduler within the vFPIO shell, which supports multiple scheduling policies, including the priority-based scheduling. So in vFPIO, we have a scheduler pair for every I/O device, like one each along the read and write path. And additionally, we support either round robin or a priority-based scheduling policy. And also, when a performance critical application wants to use when a performance critical application executes on the FPGA, we always pick we can switch to a priority based scheduling wherein its I/O request is always picked for execution. On the right hand side, next I will describe how the scheduler works in vFPIO. So firstly, the scheduler receives a scheduling priority configuration request from the host side application. And based on this, the user logics are configured as a high priority and low priority. So in this case, the user logic on the left is configured with higher priority than the one on the right. At execution time, when both the user logics hand in their I/O request to the scheduler picks the I/O request from the user logic on the left because it is of high priority, and it forwards it to the device, the I/O controller and the I/O device, and then it responds back with a completion message and any data that was requested by the user logic. So now that we have looked at each of the components of vFPIO in detail, let's take a look at vFPIO's workflow in an end-to-end manner. So firstly, the host side part of the application has to invoke the init API in the vFPIO library, through which it can offload the bit stream into one of the available slots on the FPGA's region. Please note that the bit stream has to be pre-compiled with the virtual I/O module before the offloading can happen. Next, the application invokes the open API call into the vFPIO library, and this does two things. So first of all, it performs a priority configuration into the scheduler, and it basically makes the user logic to be of higher priority in the FPGA. And additionally, it performs I/O configuration, wherein it creates an I/O path between the user logic and the target I/O device. And finally, to begin the execution, the application just calls a read or write. Based on this, the user logic, it does its own read or write request which is intercepted by the vFPIO scheduler. And because in this case, the user logic that is issuing the new request is of higher priority than the already existing user logic, the scheduler picks that and forwards it to the I/O controller for completion. So now that we've looked at the end-to-end workflow for vFPIO, next I'll talk about some key evaluation results. So in vFPIO, we aim to answer 5 evaluation questions. And due to the time constraints here, I would encourage you to take a look at the paper for the last 2 questions. So our experimental evaluation hardware setup looks like it includes 2 x86 servers, each containing their own FPGA cards. So like in our case, we use the Xilinx Alveo U280 cards. And additionally, the FPGA cards are connected via a 100 gigabit Ethernet link. And our baseline is Coyote, a shell, which is basically the shell without the virtual I/O support. So this slide shows the throughput of vFPIO for multiple applications when compared to Coyote. On the x-axis, we have the applications, which either use the local FPGA memory, the HBM, or the remote memory through RDMA. And on the y-axis, we have the throughput. And in this plot, higher is better for throughput. So we see that the virtual I/O abstractions introduced by vFPIO introduce very low performance overheads, and on average 0.7% for local memory and 1.1% for RDMA. Next, let's take a look at the overhead of switching between multiple I/O devices in vFPIO when compared to the Coyote shell. So in the Coyote shell, when the application wants to switch between switch to another I/O device, the application has to be reprogrammed, it has to be recompiled and re-offloaded to the FPGA. And in this column, we only show the time it takes to re-offload, the recompiled application to the FPGA in one of the available slots. And the way this works is that there's a process called partial reconfiguration through which the user logic is reconfigured into one of the available slots on the FPGA. So in the case of this shell, it takes around 25,000 microseconds on average, whereas in the case of vFPIO, so the reason we have a very low reconfiguration time is that because we provide a software-driven approach wherein the host side application just tries to register in the virtual I/O module, and and then the I/O path reconfiguration it takes place in the next clock cycle on the FPGA. So we basically see that the virtual I/O abstractions that's introduced by vFPIO, it enables fast I/O reconfiguration, almost like 20,000 times faster at very low performance overheads. So finally, to understand the performance isolation advantages provided by vFPIO, so we run 3 configurations of a simple benchmark that copies data between the FPGA's local memory and the host memory. So on the x-axis, we have 3 instances of the application. Now first, for the priority scheduler, we have 2 priority levels, a high and low, with 1 instance of the high priority and 2 instances of the low priority applications. And for the round-robin scheduler, we only show 1 instance. This is because the I/O bandwidth is equally divided between all 3 instances of the application. On the y-axis, we have the time to completion for each of these applications in terms of cycles. And in this plot, lower is better. So we see that the priority scheduler of vFPIO improves high priority application performance by almost 2 times compared to a round-robin scheduler. And this is essential for high priority applications. So in conclusion, we saw that for FPGA user logics on smart I/O devices, it is extremely hard to guarantee to ensure the programmability, portability, and performance isolation when more than one user logics are trying to access the same I/O device. So to overcome this problem, we introduced vFPIO, which is an FPGA-based I/O acceleration framework. So and consists of 3 components. So the virtual I/O module, it improves the programmability of the user logics by exposing virtual I/O interfaces to the application programmer. And additionally, to ensure that we can reconfigure the I/O path between the user logic and the I/O device, we provide a software-driven approach to the vFPIO library and its APIs. And finally, we include a scheduler, which in addition to round-robin policies, also supports a priority-based scheduling policy to ensure the performance isolation amongst multiple user logics during I/O device access. So our code is open source at this particular link. And I'm happy to take any questions that you may have.